All right, so this is our last recitation hour for the semester, and in the end of the semester, we are going to practice some applications related to validation of simulation models, then the output analysis modules. In our first example, the exercise set directs us to solve exercise 1.A at page 433 of our textbook banks, and it is available here. Now, we need to read the question, and we are going to discuss it a little bit because the solution procedure is very easy. And by the way, the question asks us to solve 1.A only, on the part A, then we are not going to look at part B because it's a little bit about advanced statistical procedures. It asks us to calculate the power of the test, but I mean, this is not a statistics course after all. So we are here to perform a validation procedure using a formal statistical test. Now, if you remember our theoretical hours, we have said that if you intend to perform validation on a simulation model's output, you can apply basically formal statistical tests, but also there are some other informal testing procedures, such as Turing tests. We have discussed the theory behind these kind of tests. We are focusing here the mathematical practices. So in this recitation hour, we are going to perform a validation based on a statistical testing procedure, namely a t-testing procedure. So let's read the question, and we are going to describe what we are going to do. A simulation model of a job shop was developed to investigate different scheduling rules. To validate the model, the scheduling rule currently used was incorporated into the model, and the resulting output was compared against observed system behavior. By searching the previous year's database records, it was estimated that the average number of jobs in the shop was 22.5 on a given day. 7 independent replications of the model were run, each of 30 days duration, with the following results for average number of jobs in the shop. So here the question states that there is an original system from which we have collected data from the last year, and in last year what we have seen from the system that average number of jobs in the shop was 22.5. So this information, this 22.5, the average number of jobs in the system, or in other words, work in process, or in queuing systems, in the queuing notation, you can take this 22.5 as the average number of clients in the system, was 22.5. Now, we have developed a simulation model for this system, and we have, let's just assume that we have verified it. And, you know, the verification step is mostly performed by the computer software in any way. So we are pretty sure that it is verified. The next step is to validate whether we have built a correct representation of the original system with respect to our problem definition. So we have built that model, and in that model we have run how many replications? It says 7 replications, 7 independent replications. And by independent, it means what? In each replication, we are using a different random number sequence. So they are going to be independent, even if it is the simulation of the same system. These values are independent because we use different random number streams, different random number sequences in each replication. Now, each replication is long for 30 days. However, in the end of the simulation, in the end of each replication, they have calculated the total number of jobs in the system in 30 days, and they have divided it to 30 to find the daily average number of jobs in the system. And here's the output. Now, the question is asking us this: is there any statistical proof? Is there any statistical proof to say that these values are inconsistent with the real system result collected from the last year, because we have not changed anything. We have not applied any new policy in this simulation model. We are basically trying to imitate the behavior of the original system from the last year. Therefore, if this is really a valid model, then the outputs here, the daily number of jobs in the simulation model, these outputs for 7 independent replications should be consistent with this 22.5, it says. Now, when we look at it, simply we can see that none of these values are greater than 22.5. Okay, all of them are less. Now, that may be caused by a certain bias that we have introduced in our model, unfortunately. So there may be a bias, because after 7 replications, at least we want some of these results to be larger than 22.5. By using a formal statistical testing procedure, the question asks us to validate whether these outputs are consistent with the real system output, which is 22.5. And it says develop and conduct a statistical test to evaluate whether model output is consistent with the system behavior, and use a significance level of 0.05. I have told you many times in this course that for such small sample sizes, using such a significance level, such a moderate significance level, is not a very good idea, because we have said that if you decrease the significance level for sample sizes, this will certainly increase this type 2 error of the test, statistical hypothesis testing. And therefore, if you have small sample sizes, always use a significance level that is a little bit larger, like 0.10. Okay, for moderate sample sizes, if in this question, if the question was giving us results from not 7 independent replications, but let's just say 20 or 30, in that case, we could have used a significance level like 0.05. And if the number of replications is sufficiently large enough, if it was, for example, 50 or more, in that case, you can even decrease the significance level to 0.01 safely without increasing the type 2 error or the type 2 error probability. So we are just going to follow what the question is asking from us. So we have 7 observations, and all we need to do is to conduct a t-test to check whether 22.5 can be the parent population's average for this sample. Okay, so we are going to assume that this is a sample coming from a parent population, and the null hypothesis will check whether the parent population's mean can be 22.5 or not. So let's see, we are going to follow the solution here from, again, the PDF file. Now we are assuming independence between the days, independence between the replications. And by the way, the question states that there are 30 days. Each replication is 30 days long, and we are calculating the daily average number of jobs in the system. Therefore, with these 30 days results, even the replication results or the replication averages can be said to be normally distributed. And therefore, we can safely apply a t-testing procedure even if the sample size is small. Now, our null hypothesis indicates that this sample of 7 average number of jobs obtained from 7 independent replications is coming from a parent population where the true average number of jobs in the system is 22.5. And the alternative hypothesis indicates the otherwise. And for these 7 replications, in order to check whether this null hypothesis can be true or it is false, we are going to perform a t-test, and we definitely need a t-statistic obtained with this formulation. And before applying this formulation, let's calculate the sample mean. The sample mean is obtained by simply summing up the replication metrics on average number of jobs in the system and dividing it to 7. And the sample average is 20.61 approximately. And we definitely need the sample variance, calculate the sample variance and the sample standard deviation, which are one-to-one convertible to each other anyway. So let's directly calculate the sample standard deviation. And this is the classical formula that you know from the statistics course, the sample standard deviation formula. Now, what you need to do is this. First, in order to fit this formula, you need to calculate the sample average. Okay, the sample average is definitely used in the sample standard deviation formula. Now, remember, the sample average is also a statistic. It is also another lie about the true parent population mean. Therefore, we are using a lie because we do not know the true parent population mean in order to calculate another statistic such as standard deviation. That basically decreases our degrees of freedom. And this is why we divide the sum of the squared deviations from the mean to not 7, but 6. Okay, so in order to penalize the fact that we are using another lie in calculating another lie, okay, or let me express this formally, in order to calculate a statistic from our sample, if we are using another statistic calculated from our sample, then we need to divide the sum of squared deviations not to 7. This is not simply taking the average of sum of squared deviations. We are dividing it to 6 because we need to penalize the one lie that we are telling here in the division operation. So basically, from each of these 7 values, we subtract the sample average, then we square the deviations and sum them up and divide this sum of squared deviations to 6 because the number of replications is 7. And then we take the square root of it to calculate the sample variance, which is 1.36 approximately. And now we can have a t-statistic. Now in the t-statistic, we need to look at the difference between the sample average and the recommendation on the right-hand side of the null hypothesis. So our sample average is 20.61 and the recommendation of the null hypothesis is 22.5. There is a certain negative difference between these two values. However, we need to standardize this difference because it comes from a sample for which the sample standard deviation is 1.36 approximately. So we need to standardize this difference to convert it into a statistic by dividing it to the standard error, my friends. Okay, what is standard error? The standard error is the sample standard deviation divided by the square root of the sample size. Okay, so sample standard deviation is 1.36 divided by the square root of the sample size, which is 7. You get a t-statistic after dividing the deviation of the sample average to the suggested average of the true parent population. We divide it to the standard error, and that value, my friends, is minus 3.68 approximately. Okay, this is our t-statistic. Now, if this t-statistic is very large, okay, but both in negative or positive sides, it doesn't matter because this is a two-sided hypothesis testing. If this t-statistic is very different from 0, then we need to reject the null hypothesis, okay? Because the difference between the sample average, sample mean, and the suggested mean of the true for the parent population in the null hypothesis is too different from each other. However, if this t-statistic is close to 0, in that case, we cannot reject the null hypothesis. We say that there is not enough evidence to reject the null hypothesis, and we cannot reject it. Now, obviously, in order to make this decision, we definitely need a critical t-value to compare the absolute value of our t-statistic, okay? So the absolute value of our t-statistic is 3.68 approximately, and we need to compare it with a critical t-value. And this critical t-value is obtained by using the significance level assumed by the question. The question recommends us to use a significance level of 0.05, and because this is a two-sided t-test, we need to take the half of the significance level to split the error that we can make to both sides of the t distribution. As it is a symmetric distribution, we can only check one quantile at 0.975. Okay, half of 0.05 is 0.025. And if we identify the 0.975 quantile of the t distribution with degrees of freedom 6, obviously, okay? So n is 7, my friends. The sample size is 7, but we need to check the degrees of freedom parameter as 6. For degrees of freedom parameter 6 and the 0.025, we need to look for the percentage points of the students' t distribution for 6 degrees of freedom and for 0.025 tail probability. That tail statistic is 2.447. Now, if we go back, that is consistent. The solution here is consistent with the t-table result, and we can say that the absolute value of our t statistic is definitely greater than the critical t value here, which indicates that there is enough evidence to reject the null hypothesis, which means there is no way with these replications, with this simulation model, there is no way of saying that the number of jobs in the system in the simulation model is averaged at 22.5, my friends. Okay, so this indicates what? This indicates the model outputs are inconsistent with the real system output. Therefore, there's a certain discrepancy between the model that we have developed and the original system with respect to the performance metric that we are considering here, which is the number of jobs in the system. Therefore, we need to update our model. Okay, so this statistical test shows us that there is a certain bias caused by the assumptions that we have made in the simulation model. Then some of these assumptions may be relaxed, or there may be some other facts in the original system which is related to our problem, but we have not introduced in our model yet. Maybe these kind of facts should also be introduced in our model to make this result consistent. Okay, now I should also say that this is just trying to check whether the average number of jobs in the system collected from the last year is consistent with the average number of jobs in our simulation model. Now, let's just say in the end of this t-test, we couldn't have rejected the null hypothesis. So does this mean this is a valid model? Unfortunately, no, my friends. I mean, you can say that with respect to this performance metric, with respect to the average number of jobs in the system, there is no inconsistency, we say. There is no statistical proof to reject the consistency here, we can say. However, we need to check maybe other statistics as well, not just average number of jobs, but the average waiting time of jobs in the system. We need to perform a validation procedure over that output variable as well. Okay, so we cannot simply say that just because one system output is consistent with that corresponding output in the simulation model, we cannot simply say that this model is a valid model. We need to perform this procedure for other outputs as well. But I mean, each procedure is simple here. And by the way, this procedure is trying to check whether the average number of jobs in the system is consistent with the average number of jobs in the simulation model. But maybe you can also perform an f-tests, or in that context we should say chi-square test, because I mean, let me describe what I want to tell to you. Sometimes we do not just check the average number of jobs in the system, but the sample variance of the daily number of jobs in the system with the sample variance obtained as an output of the simulation model. Okay, we do not always perform the whether the average of the certain performance metric is consistent with the real system results. Okay, sometimes we check the variances as well, and if you want to check variances, then you need to use a chi-square test. Okay, so please do not think that by simply checking the average values of the performance metrics, the validation procedure is perfectly performed. Sometimes we need to check other statistics, such as the variance of the performance metrics, whether they are consistent with the variance of these metrics obtained from the real system output. But in that case, you do not perform a t-test, but you perform a chi-square test, right? So please keep that in mind. Everything that you learn from the statistics course are useful in the validation procedures, not just one sample t-test. I mean, because this is not a statistics course, I just want to show you how we can practice a statistical validation procedure in this question. And that is the end of the question, my friends. I'm not going to solve anything further. At this point, I'm going to stop recording.